Hello. After covering steady-state AC power and also coupled inductors, we will today cover a special case of coupled inductors, which is very important for power transmission. Transformers are usually used to step up or step down AC voltages and currents. Power plants generate voltage at around 10 kilovolts. Transformers step up this voltage to around 200 kilovolts or even more for transmission over long distances, because when we increase the voltage, the current decreases and that way the line losses decrease. And at the receiving side, at the substation, transformers are again used to reduce the voltage from 200 kilovolts to 110 volts or 220 volts, which is what the customer needs. Let's have a closer look. Here is the super simplified model of the power grid. We have a generating station, which might be a hydroelectric power plant. We have a generating step-up transformer, which is basically connected to this power plant just next to it, where the voltage is being increased to 300 kilovolts or more. Then we have the transmission lines, which might be at different voltages, but all of these are over 100 kilovolts and more. And we just have here some type of a substation, maybe at the entrance of a town or at the entrance of a factory, which decreases this 300 kilovolt voltage to 26 kilovolts or 69 kilovolts for factories or big power plants such as arc furnaces for smelting, or decreases it, reduces it to 120 volts or 240 volts for the usage of the customers to watch TV or wash your clothes. With respect to secondary customers, basically the electricity which we can get from the wall, we have two fundamental electrical systems around the world. One of them is the 110 volts, which is actually covering the range from 100 volts to 127 volts. And the other one is 220 volts, which actually covers the range from 220 volts to 240 volts. Both of them have a variance for 50 Hz and 60 Hz frequency for the AC voltage. And the 220 volts is more or less the whole world except North America, some parts of South America, Saudi Arabia, and Japan, and all the rest of the countries are using the 220 volts. But this is important because devices which have been designed for 110 volts might not work for 220 volts. Even though right now many of our devices such as laptop computers, etc. have adapters which can reduce the voltage from 120 or 220 volt AC to 12 or 19 volts DC. That might not be the case for your electric oven. Therefore, you need to be careful when you bring some type of electrical appliance from one of the regions to another region. Another practical aspect which you need to be careful about in electrical engineering is the type of electrical plugs. So in Europe, Russia, Kazakhstan, Turkey and Iran, and in some other countries, we are using the European type plugs, which are called type C, E, and F. In other countries around the world, for instance, in India, we are using type D. In North America, we just have type A and B. And therefore, you cannot directly connect electrical appliances, electrical devices from these different regions without using adapters easily to the wall. Now we know the importance of transformers in the power distribution systems across the world. Let us figure out what is an ideal transformer. An ideal transformer is a model of a transformer with the coupling coefficient equal to unity. The coil connected to the power source is called primary coil. The coil connected to the load is called the secondary coil. N1 and N2 are the windings of the primary and secondary coils respectively. The constituent equations which govern the behavior of a transformer is V2 is equal to N2 over N1 times V1 and I2 is equal to minus N1 over N2 times I1. So N2 over N1 is equal to N, which is the turns ratio of the transformer. And I would like to reiterate once more that transformers are only used in non-DC applications because at steady state in DC, the coils act as short circuits. In the frequency domain, using the phasors, we can write the mathematical equations for the transformer as ideal transformer as V2 is equal to N2 over N1 times V1 and I2 is equal to minus N1 over N2 times I1. So here in between the transformer coils, we are putting these vertical lines, and these vertical lines denote the iron core or the ferrite core of the transformer. And we also write ideal to show that the coupling coefficient of the transformer is unity. So that's why it is an ideal transformer. The ideal transformer is usually placed between a source and load, and usually it increases the voltage level from V1 to V2, which is adjusted by the turns ratio. In other words, N2 over N1. How many windings we have on the secondary coil versus how many windings do we have in the primary coil. And we can also draw this circuit in the frequency domain as shown here in the bottom part of the slide. The input to my ideal transformer circuit is V1, which is the voltage source of the primary coil. The input impedance of the circuit connected to the voltage source can be given by V1 over I1 as Z1. And Z1 is called the impedance seen by the primary coil of the transformer or the impedance seen by the source. The ideal transformer, which is a lossless device, can be represented by the following equations. V1 is equal to V2 over N and I1 is equal to minus N times I2. Similarly, we can write the following equation for the secondary coil. V2 is equal to minus I2 times Z2. Here we have this minus sign because the I2 does not adhere to the passive convention. It is entering from the negative terminal of the impedance Z2. So far we wrote 4 equations related to the ideal transformer circuit connected to the source and a load. The input impedance, the relation between the voltage of the primary coil and secondary coil of the transformer, the equation which relates the currents of the primary and secondary coil, and also an equation from which I can find the impedance of the secondary coil as Z2 is equal to V2 divided by I2, but with a minus sign. And using these equations, I can write Z1 is equal to V1 divided by I1. And I can use for V1 the following equation, V2 over N. And for I1, I can write minus N times I2. And since minus V2 over I2 is equal to Z2, then Z1 is equal to 1 over N squared times Z2. This is an interesting result. So, in general, we can tell that the source of the circuit experiences the impedance Z1, which is actually the impedance Z2 reflected to the primary coil of the transformer. So, if I were to convert this circuit to a circuit with a single impedance and no transformer, then I would have the following circuit where the voltage source is directly connected to the equivalent impedance, which is N1 over N2 squared times Z2. Okay, now we will solve an example on maximum power transfer in a transformer circuit. And we need to find the value of turns ratio N in order to have the maximum power to be transferred to the load with RL is equal to 8 ohms. So what I will do is that I will draw this circuit in a way that this RL will be reflected as an impedance to the primary coil of the circuit. Accordingly, the equivalent circuit will be plus minus V1 here. Here I will have RS. Then I will have my reflected impedance, which will be RL over N squared. And this will be my equivalent circuit without the transformer. And in order to have the maximum power transfer, RS should be equal to RL over N squared. And if I plug in the numbers, I have 48 is equal to 8 over N squared. And from here, I get N is equal to, if I am not wrong, 1 over square root of 6. So basically, I need to have this turns ratio, which is equal to N2 over N1, N2 being the number of windings in this coil, secondary coil, and N1 being the number of windings in the primary coil, as 1 over square root of 6, such that we have the maximum power transfer to the load resistor. So this was quite simple. Alright, in this question I need to determine the output voltage V0t for a sinusoidal input voltage, and this circuit is in the time domain, so I will first convert it to the frequency domain by writing Vs is equal to 75.5 with an angle of 26 degrees. 8 ohms will be 8 ohms. This current will be the current phasor I, and V will be V out phasor, and this 9 Henry will be 9 times 4, 36 J. So that is the impedance, because the impedance for an inductor is J omega L, and omega is here 4. And now the second step will be that I will find the combined impedance here, which will be equal to, I will call this Z2, 30 plus J36. And I will now redraw this circuit, this time by reflecting this impedance to this side, and it will be Z equivalent, which is equal to 3 over 2 square times Z2, and this is equal to Z equivalent 9 over 4 times 30 plus J36. And if I calculate this further, I find this equal to 9 over 4 is 2.25. 2.25 times 30 is 67.5 plus 36 times 2.25, which is, if I am not wrong, J81. So I found this equivalent impedance. Now let me redraw this circuit. The current in the primary coil is defined, but not in the secondary coil. I will define that current as I2. Now let us draw the equivalent circuit in frequency domain, 75.5 with an angle of 26 degrees. Here I have 8 ohms. Here I have the equivalent impedance 67.5 plus J81. And I have the mesh current I passing through this circuit. I can calculate here I simply as the voltage phasor for the supply, 75.5 26 degrees, divided by the total impedance of that circuit, 75.5 plus J81. And if I write the bottom part in the polar form, I will get the following. 101 times 0.7 with an angle of 47 degrees. And if I do some complex algebra, I get I is equal to 0.68 with an angle of minus 21 degrees, and the units of this will be amperes. So far so good. Now I know the current in the primary coil, and I can calculate the current in the secondary coil using the general equations for the ideal transformer. Alright, I2 will be equal to minus n times I, which is equal to minus 3 over 2 times 0.68 with an angle of minus 21 degrees. Accordingly, I2 will be equal to minus 1.02 with an angle of minus 21 degrees. And I will find V out as 36J times I2. But wait a second, let's be careful here. Here the positive polarity of the V out is here, and current I2 is exiting that, so therefore it is not adhering to the passive convention. Therefore I need to put here a minus sign. Accordingly, this will be equal to minus 36J times minus 1.02 with an angle of minus 21 degrees. And V0 accordingly will be equal to 36.82 with an angle of 69 degrees. And I can easily convert this to the time domain as 36.82 times cosine 40 plus 69 degrees. And this way I conclude the solution of my question. I find the output voltage V0 for this circuit. In the beginning of this lecture, we have told that we are using transformers mainly for power transmission. We are generating power at a power plant, and we are using step-up transformers to bring that voltage to a higher level, such that we just carry it using low amount of current over transmission lines to long distances. And we use step-down transformers to decrease it to a lower voltage such that the customers can use it for varying purposes. The second application area of transformers is galvanic isolation. Galvanic isolation is a method of isolating parts of electrical systems when no direct conduction path is permitted. For instance, this is very common in medical devices. If we connect a medical device to a person in intensive care unit, we do not want to physically directly connect a human being to the wall where there is 220 volts. Imagine that there is a short circuit in the device and the wall is directly connected to the person, which would be catastrophic because it would cause an electrical shock. In these type of circumstances, these medical devices are using galvanic isolation, either using induction transformers or using optical means, for instance, optocouplers. When we need to connect two electrical circuits with different ground potentials, we use usually galvanic isolation. This way, the flow of unwanted current between two parts sharing a ground conductor is prevented. And galvanic isolation is also used for safety, preventing accidental current from reaching ground through a person's body. So, in general, in galvanic isolation, if we want to deal with power, we are using transformers. And if we are dealing with digital circuits, or in other words, with signal processing, we are using optocouplers, because optocouplers can only transfer information using very little amount of power, but they cannot transmit high amount of power.